bell's going, that's perfect. Yeah. Clearly I'm jumping the gun. Okay, welcome everybody. I'm David Abrahams. I'm the director of the Newton Institute, and I'm the warm-up for the warm-up. So it's my pleasure to welcome you here, and especially our Rothschild distinguished visitor. So for those people who aren't familiar with the Newton Institute, we run research programs, typically of 4 or 6 months duration, and each one has one eminent researcher who's invited to be the Rothschild distinguished research visitor. They normally stay for a month, and even though we give them this title, they usually work harder than anybody else, giving lots of lectures, and the culmination of all that hard work is the Rothschild lecture itself. And this is one such lecture today, and it's my pleasure to welcome Professor Weickert from Saarland University, and he will get our official welcome, an introduction from Carola, who's one of the organisers of this program. So welcome, and I hope you enjoy the lecture, and thank you for your visit as well.
Okay, welcome everybody. It's my great pleasure to introduce Joachim Weickert from Saarland University. And before I'll hand over the stage to Joachim, I'll just say a few words about him. I hope I don't embarrass you, Joachim, but I think it's good to say a little bit about you. So Joachim is a professor of mathematics and computer science in Saarland University. He is also head of the mathematical image analysis group, short MIA. He started his career in Kaiserslautern, where he got his PhD. He then moved to Mannheim for his habilitation, with various research stays, for instance, in Utrecht and in Copenhagen. His research is in image processing, computer vision, and scientific computing. He's very well known for pioneering work using techniques based on partial differential equations, variational principles, wavelets, morphological and non-local methods. And over the years, he has developed mathematical models and efficient numerical algorithms for various image processing and image analysis applications, for instance, for image restoration, enhancement, segmentation, compression, as we will hear about today, optical flow, stereo reconstruction, shape from shading, as well as signal processing methods for tensor fields. And his ideas have entered various applications in industry, in biomedical image analysis, and many other fields, forensics, for instance. I also know about fingerprint enhancement. And on these topics, he has written more than 300 publications with over 22,000 citations. And his research has been honored with various prizes and awards. I'm only going to name a few of the honors that he received. One of them is that he is editor-in-chief of the Journal of Mathematical Imaging and Vision. He received the Leibniz Prize, which is the highest prize in Germany, the highest research award that one can get. And very recently, actually this year, he received an ERC advanced grant in COVID. Yeah. And he was is also elected member of the Academy of Europe. So without further ado, we are really honored that he spent this month here with us, and that he will finish his visit with this lecture today on image compression with differential equations. Thank you very much, Joachim.
Thank you very much for the kind introduction. It's a great pleasure being here and enjoying the fertile atmosphere of discussions here. Yeah. What is this talk all about? First of all, I should say that this is long-term research that has been funded by this Leibniz Award and also a seamless continuation with the ERC grant. It helps me basically to pursue this research topic for about 12 years, and I would like to summarize a little bit my view on these kind of things. Yeah, this is probably the most inappropriate phase to start a talk with at the Isaac Newton Institute. Nevertheless, here are some other faces. These are my collaborators. Some of them were PhD students, postdocs. Some others are colleagues from Germany, France, Croatia, and Norway. And so this is joint work with lots of people over a period of about 10 years, and it's still going on. And what is it all about? Well, actually, I would like to start with a dream. If you look at your laptop and look at your files, what are the big files on your laptop or on your computer? These are usually files with extensions just such as JPEG, perhaps MPEG or MP4 or something like that. On the other hand, many of you, if you work in applied math, are dealing with partial differential equations. So wouldn't it be great just to have a file extender which is simply PDE? Then every student would be curious to learn about that strange file format and would join your PDE classes. So that's the dream. And let me try to convince you that this is perhaps even an interesting way to go. So I would like to start with something which is relatively well known in the image analysis community. That's a concept called inpainting. For the people outside image analysis, just call it interpolation. It's the same. So what you see here is an image of New Orleans before the flood. And this image has been degraded here by lots of red letters. Now what you can do is basically you can regard these red areas as areas where you solve elliptic partial differential equations such as an anisotropic diffusion equation, and you can use this data which you have here as kind of Dirichlet boundary conditions. So you fill in information by solving a diffusion or heat equation, and what you get is something like that. Looks pretty convincing. So if I would have shown this image to you, you would have seen nothing suspicious at first glance. So that was the state of the art about 20 years ago. And then I always like to drive ideas and concepts to the extreme. So I was wondering what happens if we increase our inpainting domain here from a few percent to, let's say, 98%. So for instance, here I took a grayscale image and I have just removed randomly 98% of all pixels. And now the question to you, to everybody who has not seen this before, is can you recognize what is depicted here? No idea?
No idea.
Sometimes the answers depend a little bit on the season. More towards Christmas time, people have already seen Joseph and Mary and little boy child Jesus in between. But also this is wrong. So let me tell you what I'm doing. Imagine this is a room, and the pixels which you see are small air conditioners which I have placed randomly in the room. And the gray values which you can recognize here are just the temperatures at which I have fixed the air conditioners. And now I'm computing the stationary temperature distribution, so I'm basically evolving the heat equation over time or the diffusion equation over time, and I'm using an anisotropic one, and what I get is this.
May I just quickly ask, it's difficult to see on the screen, but in the grey area, are all the grey pixels the same shade of grey?
No. They have different shades of grey, which correspond to their grey values. Grey values are just the function values here. What you see is you get a reconstruction of the face of a lady, just using a simple diffusion equation. When I saw that about 10 years ago, I thought, well, okay, here things have been chosen in a random way. What would happen if I put a little bit more brain in the selection process? So for instance, here's a first attempt when I was younger, as you can see here on my face, a first attempt to select the data a little bit more semantically. So I took here the original image of myself, and I discarded all the information apart from the color values left and right to the edges, to the so-called canny edges, so basically locations where the gradient magnitude is large. So these are all the data which I have. And now in the white areas, I'm solving one of the simplest partial differential equation you can think of, namely the homogeneous diffusion equation. Basically, Laplace u equals 0 for the steady state. What I get is this. So it's an almost perfect reconstruction. It's perhaps a little bit too smooth, so you can argue that this is kind of digital Botox, and I would not disagree. So that's the essential idea, basically. So I would like to remove most of the data from images, keep only a small percentage of carefully selected data, and interpolate in paint in between using partial differential equations, in particular of diffusion type. And for those of you who don't have an image analysis background, let me give you a few basics that we need in order to understand that talk, in particular about continuous and discrete images. If we have a rectangular image domain, let's say omega in R2, then a grayscale image in a continuous case is nothing else but a scalar valued mapping from omega into the real numbers. If you have a color image, you have 3 channels, red, green, and blue, so you basically map into R3. What you experience in practice, however, are digital images, and they are discretized in 2 aspects. They are discretized in space. This is what people call sampling. So you have a regular pixel grid. And what is less well known, they are also digitized or discretized in their gray values. This is called quantization. So typically you represent your gray values by 1 byte, so that means 1 out of 256 values. And if you have a color image, so you have 3 bytes to represent 1 color pixel. And if we talk about, let's say, 60 megabytes, so this means we have 60 million pixels with 3 color channels. Each color channel is 1 byte, so that would easily occupy 48 megabytes to store this amount of data. And it's clear that's not what you want. You want to compress the data, and so it's very natural to look into compression ideas. And in general, if you want to achieve large compression rates, so that means a large decrease of your file size, you are interested in so-called lossy compression methods. That means these are inexact compression strategies which are still so good that you as a human being are completely satisfied with the quality. The quasi-standard these days, which you all know, is JPEG. And the idea behind JPEG is you basically decompose your image into small 8x8 pixel patches, and in these blocks, in these 8x8 pixel blocks, you can assume that your image is relatively simple and homogeneous, and within each block you do kind of a frequency analysis by means of the DCT, the discrete cosine transform, a variant of the discrete Fourier transform. And essentially what you can do is the higher frequencies can be stored with less precision. You don't see imprecisions in the higher frequencies, so you use this for coarser quantization, which saves a lot of bits. And that's the main mechanism behind JPEG compression. And this works relatively well if you have compression rates in the order of 10 to 1. If you go substantially beyond 10 to 1, the quality deteriorates a lot. So here's an example. That's the original image of the lady. Now we compress this image with 10 to 1. So here's the original. That's the compressed version. So you hardly see difference. Original, compressed, 10 to 1. If you go to 40 to 1, you clearly see the 8x8 pixel blocks. And if you go to 80 to 1, it looks poorly. And nevertheless, it would of course be very interesting, given the high amount of data that we can easily produce, to come up with compression methods which work well also with compression ratios of 80 to 1, or perhaps even beyond. To this end, people have been thinking about successors for JPEG, such as the wavelet-based JPEG 2000, which works somewhat better. I would like to go a completely different way. I would like to focus completely on partial differential equations, in particular of diffusion type. And the idea was clear. You keep only a few selected pixels and you interpolate the rest. This idea sounds very simple, however, it gives rise to a few very challenging questions. First of all, what are good pixels to choose? It's obvious that not all pixels are equally good or equally bad for that purpose. Secondly, what is a good in-painting operator? What is a good differential operator to interpolate data in such a way that the data is supposed to look like the data which you have in natural images? And once you have found your pixels and you have agreed on a certain in-painting operator, you still have to code the pixels afterwards. And encoding the locations is not that cheap, so you have to put also some extra efforts in encoding this data. And to make things worse, these type of problems are highly interrelated. Obviously, the optimal pixels depend on your differential operator. That is to be expected. But it can even happen that perhaps you can get some pixels so cheap that you simply cannot refuse that offer. If there are pixels on a certain regular structure on a grid, for instance, of course I don't have to encode their location. So that means sometimes pixels are so cheap that it's better to accept the offer of using suboptimal pixels rather than using optimal pixels which are more expensive. And that means we have to deal with lots of kind of compromising and kind of contradicting optimization problems. And before I tell you more about the structure of my talk, here's a little review of related work. In-painting is something which is around in the image analysis community since about 2 decades. It started with Masnou and Morel, and lots of subsequent work has been done in that direction, also here in Cambridge with the book of Carola. In general, these in-painting methods just use in-painting for removing scratches, so that means you are given some certain degraded areas, and typically these areas are relatively small compared to the areas where the image is not degraded. So that means you don't deal with very sparse data. In general, you don't take the liberty to optimize your in-painting data. There's also some work on using diffusion to reconstruct an image from some features, such as edges, for instance. However, most of these people have not been going so far that they were daring to use this for compression, because there you're really aiming at high quality. And there are some papers on PDEs for image compression, but they are mainly focused either on very specific applications, for instance, depth maps in stereo images or digital elevation maps, or they take an existing codec, such as JPEG, and try to replace some of the modules, some of the ingredients by some PDE-based ingredients, but it's not redesigning something from scratch. This is more the goal which I would like to pursue. So we built novel codecs based on in-painting-like ideas, in particular with PDEs from scratch, and basically design everything by ourselves. Here's one of my strongest motivation. About 12 years ago, I had a discussion with Stan Osher, a very famous numerical analyst, and he said, forget about these things. It will never work. You can never beat JPEG and JPEG 2000. And as you know, science and stubbornness start with the same letter. So that's, of course, a strong motivation to disprove him. So let me report a little bit about the efforts in that direction. So here's the structure of my talk. So it's clear we are dealing somehow with optimization problems, in particular data optimization. I would like to do this first in a completely continuous setting, and secondly in a discrete setting. And then I will do something which is perhaps less obvious. I will also try to optimize the gray values. This is what I call tonal optimization. So that means I'm also optimizing the codomain, not only in the domain. Yeah, so much about data optimization. Then I would like to find suitable in-painting operators. So we talk about good PDEs for in-painting. And last but not least, I would also like to discuss encoding strategies with you and give you also a brief review of lots of possible extensions and applications. So let's start with the continuous problem, and let's try to optimize the data. So our continuous model is relatively simple. We are given some, let's say, grayscale image to keep things simple. And we know it only in a small subset of our rectangular image domain omega. So the known subset is denoted by K. And there we know what to expect. So our in-painted solution is identical with the gray values of the original image. And let's say in the area where I don't have any data specified, I just want to in-paint with one of the simplest PDEs available, the LaPlace equation. It's a linear equation, it's simple. I have a chance to do something analytically in that setting, and that's the reason why I would like to consider it in the first part of my talk. So basically, what I'm doing is nothing else but solving an equation like that with a confidence function which is 1 in the known pixels and 0 in the unknown pixels. So if C is 1, then this term vanishes, and I know that U equals F, so that's my interpolation condition. And if C is 0, then I have no confidence in my data there, so this term vanishes and I'm solving the Laplace equation. No? So that's just a rewriting of what I'm doing. Okay, can this be optimized? First I was skeptical, but then I met Dorin Bocour and Zakaria Belachmi, 2 experts on shape optimization, and we joined our forces and we came up with a theory, with an analytic theory of data selection using principles of shape optimization. This theory is very complicated. I would like to refer you to a Zyme paper if you want to read all the details. Here is, in a nutshell, what we have been doing. We have been considering different models which differ by the way how you approximate your error, or the way how you measure your error. So if you are using LP norms or Sobolev norms, for instance, and also the way how you measure your known data set K. You can use Lebesgue measures, Hausdorff measures, or more complicated concepts. However, all these different models have one thing in common. Basically, the pixels which I'm modeling in my continuous setting are pixels which have a non-zero area. So that means they are fat pixels which have a real positive area, so you can think of them as, let's say, disks, for instance.
When you say positive area, does this imply that each pixel itself has a small area?
Yes, yes. You can think of it as a little disk or a little square, for instance.
Okay.
No? Because otherwise, if it has an area of 0, some of these problem formulations simply don't make sense. The theory is quite horrible, but the outcome, the result is very simple. The result that we got is essentially a simple suggestion, namely, choose the density of the data points which you want to have as an increasing function of the Laplacian magnitude. That's all. It's extremely simple. And the nice thing about that is you can immediately put this into practice. For instance, take this image which depicts the mathematician Felix Klein, compute his Laplacian magnitude. So the dark areas are the areas where the magnitude is large now. And that should give me the pixel density. So that means I should place more pixels at those locations where the Laplacian magnitude is large. This is a well-known concept in image analysis. There are methods which are called dithering methods that do exactly that. And it looks like something like this here, for instance. So these are 10% of the data points which I'm going to keep here. And if I know the gray values at these data points and in-paint in between by solving the Laplace equation, what I get is this. And that's exactly what theory predicts. So we put it into an algorithm literally, and it works. And the funny thing is, it's so simple that it's even possible to do this in real time here on a small laptop. So let me show it to you. So I'm now taking images of myself continuously, something like 15 times or 12 times per second. And I have here just a simple laptop CPU. I'm not using any GPU or any tricks with parallelization with graphics processors. And I take some standard dithering algorithm, and let's have a look how this works. Okay, yeah, here we go. So on the top left, you see me moving around. On the top right, you see my Laplacian magnitude, so that means here it's bright where the curvature is high. And on the bottom left, you see the pixels which I select according to this Floyd-Steinbeck dithering. And on the bottom right, you see the in-painting using homogeneous diffusion, the Laplace equation. So if I increase the number of my pixels, the quality should become better. Now it's almost perfect. And if I decrease it, it should deteriorate. Now the big question is always, is my face more important than my shirt? Well, I should have worn a shirt without stripes. Okay, but you see the basic principle. Huh? However, you have also to work a little bit numerically here. You have to use multi-grid algorithms. You have to optimize these things, otherwise it doesn't work. Yes?
Do you actually measure the difference between the original and the in-painted?
You can do this, yeah. You would use a simple L2 norm, for instance, a Euclidean norm, yeah.
Nice to see, because
Um,
we're not as good in seeing the differences.
Well, you use these measures in particular if you want to publish papers. All the engineers force you to do so, and you have to be better than the JPEG and JPEG 2000 standards. So it's a big trouble, believe me. It's not enough proving theorems to satisfy those people. But nevertheless, you see, essentially it works. It works even in real time here. And well, you could say this is the point where we could stop the talk. We are done. But of course, you see, we have lots of slides to go. So, what's the issue here? Well, first of all, let me show you that it works and that it's good. So, if we take our image of the lady and we would select, say, 5% of the pixels randomly, in painting with the Laplace equation gives us something like that. And here's the error that we talk about. So, the mean square error, that's basically a normalized L2 norm, is 189. If I use here this analytic theory based on the results from shape optimization, I can decrease the error easily by factor 4. So that shows that things are already pretty good, and you see the result is not so far away from the original image, but of course the question is, can you do better? This is not competitive to JPEG yet. So where are the problems? How could we improve these things? Well, first of all, the nice thing is we have a clean analytic theory that works. What's not so nice is, of course, you have to put this clean analytic continuous theory into discrete practice. To this end, for instance, you have to use this dithering. This introduces errors, even with the very best algorithms. So that means we are clearly losing here, and depending on the different models which we have chosen, you get different suggestions. What is the increasing function of your gradient magnitude? Here I've just chosen a linear function for the sake of simplicity. So that means we have some room for negotiations here. So a natural question would be, perhaps I can do better if I model everything right from scratch in a completely discrete way. So let's try this as an alternative. So discrete spatial data optimization, that's the next topic. And this was our continuous model, no? With a confidence function C, which is either 0 or 1. And if you discretize this, your functions turn into vectors. The vectors contain the gray values in the pixels. And your function C here turns into a diagonal matrix, which is either 0 or 1 on the diagonal, depending on whether your data are not known or whether they are known. That's all. So basically, the nice thing is we have to solve essentially this equation for U, and you can easily rephrase this as a linear equation, as a linear system of equations which you have to solve for U. And what does this mean? Well, the A here, the A is a discretization of the Laplacian. So that means this matrix tells you which kind of in-painting operator you have chosen. The C is your confidence function, so that's the pixel mask you are going to select here as the data which you want to keep. And you have one more degree of freedom, namely the F. The F is the original data of your image. Perhaps you can even modify those a little bit. So basically, the task is to find the best hue given a certain percentage of pixels which you have to select. That's the task of selecting your C, and you even have the liberty of choosing your A. So that shows you that this is a problem with lots of degrees of freedom. And the first one I would like to deal with is optimizing the mask C. However, if we are facing such a linear system, it would be natural first, because we are mathematicians, to ask whether it has a solution at all and whether this can be computed in a nice and stable way. So here's the first result, and the result is as good as it could be, basically. It tells you that it's enough to specify a single pixel in your image as a Dirichlet data, and then the problem has a unique solution. It doesn't tell you something about the condition number, but the solution is unique, and it even satisfies a maximum-minimum principle, provided that you are using here your discrete LaPlace operator. So that means that you are dealing with homogeneous diffusion in painting. So in other words, the inverse of this matrix exists, and I have here a nice unique solution. Secondly, basically, if you're a pure mathematician, you can be happy at that point, because you know it's a finite problem, and selecting, let's say, the 10% or the 5% optimal pixels is a finite combinatorial problem, so it will have a minimum. So the minimum exists. Perhaps it's not unique. It's a finite problem, so we could all go home. That's very simple. So that's the good news for the pure mathematicians. The bad news for the applied ones is, well, yes, it's a finite problem, but you have lots of options. So if you have ever played lottery, this is far worse. Lottery in Germany means you have to select 6 out of 49 numbers. I don't know how it is here. Similar. So here you have to select, let's say this is a small example. Let's say an image of size 256 by 256, so we have something like 65,000 pixels. And if we are planning to select 5% of them, you have an astronomically large number of possibilities. So life is simply too short to try them out. No? So you need a good strategy. There are many strategies available. A simple one, which is easy to explain and works nicely, is as follows. It's also historically the first one that we have been pursuing. It is probabilistic sparsification strategy. You start with all pixels, and then let's say you nominate randomly 10% for being thrown out. Then you just remove them, and you look how nice life is without this 10%. So you compute the errors at the locations where you have removed the data. If the error is large, then the pixels were important, so put them back. If the error is small, the pixels were not necessary, so you accept that you have removed them. And you do this iteratively, so this is basically a greedy algorithm that tries to find a minimizer. So that's the strategy. And of course, the big drawback of all greedy algorithms is they are nice in the beginning, and towards the end they become worse, and they may get stuck into local minimizers. So you need some sort of a post-processing step that tries to avoid getting trapped. For instance, you can exchange your masked pixels with randomly selected non-masked pixels where your error is large. Yes, Andrew?
Is 5% a sort of realistic target to beat JPEG?
Yes, perhaps you would even aim at 3% or something like that. Yeah. Actually, we are looking into small amounts of pixels because you want to beat JPEG at the high compression rates. For the low compression rates, JPEG is doing perfectly fine. Even JPEG 2000 is not better at that rate.
And sorry, and what percentage number is that? Is like 1%?
Well, it's not that easy to say, because you also have to encode the location, and encoding the location is very, very expensive, actually. I'll come to that point later on. Okay. So this is a heuristics, but it works surprisingly well. Actually, there are far more refined strategies, for instance, bi-level optimization strategies. Our group has been looking at that, but also people around Tom Pock and people in Italy. The quality does not differ that substantially. It's mainly an issue of speed, how efficient these algorithms are. Let me show you what you can get. So once again, our test image, 5%. That was the best we had so far. Our analytic theory suggests this approach. And if we use a discrete theory, where we are certainly not ending up with a global minimizer, but a local one, our local one from the discrete theory is far better than the global one from the continuous theory, because we have to put this continuous theory also into discrete practice. So that means it pays off looking into these discrete stories. Okay. Is this the end of the road? That's almost, well, the initial mean square error was something like 190, so that's almost a factor 10. Is this the end of the road? Well, luckily no. We have one more option, at least one more, namely we can optimize the gray values. What does this mean? Well, so far what we have done is we have basically our initial image, and we had this reconstruction function, which is nothing else but this one here. That's the inverse matrix applied to the data which I have. This reconstruction function has been optimized with respect to the mask C, or at least the first attempt to optimize it. We have not optimized it with respect to F, with respect to the gray values. And the nice story is it's highly nonlinear in C, but it's linear in F. So that's actually a pretty easy story to optimize the gray value. So we can just add a perturbation of the gray values, let's say a perturbation vector alpha, and try to solve a problem which tries to optimize this perturbation vector alpha. And the nice thing is this is a simple least squares problem, and that means we can essentially solve it with some standard tools. One has to put a few considerations into it to show that it has a unique solution, but that's not too difficult actually. So essentially you have to solve a least squares problem. You can do this, for instance, with a randomized SOR algorithm which just selects the pixels, optimizes them, and selects randomly the next one. You can also do much more refined things here in later papers. They give rise to faster algorithms, but they don't change the quality. It has a unique minimizer. No? What do we get from optimizing the gray value? So what is the hope? Obviously, in the pixel itself, I'm doing worse if I optimize my gray value, because the correct pixel, the correct gray value is the best in the pixel itself. However, in the neighborhood, I might be able to do better. If I lift my pixel up and down, perhaps I improve the approximation quality in the neighborhood. And of course, I want to have a good average approximation quality, so I can expect that I can do better. And actually, that's the case. So here are our spatially optimized results randomly. This is the analytic theory, and that's the discrete theory. These are the errors which you have. And if you supplement these locations with optimized gray values, you see that the error can decrease, sometimes even dramatically. You know? So here we get almost a factor 2. Here we get perhaps 20%. But nevertheless, that's of course a nice story, because for me it's just as expensive to encode an optimized gray value than to encode a non-optimized gray value. No? So that's a simple story. So that means grayscale optimization, or tonal optimization, how I call it, is something which is also very useful, and it helps you to reduce your error by more than a factor 10. And that's a typical number which you can observe here. Okay, that was the second story of data optimization, spatial and tonal optimization. Now let's talk about the differential operator. That's also a degree of freedom, and what we have done so far was we took the simplest candidate, the LaPlace equation. Nevertheless, this is even pretty good if you do a good job in optimizing your data. Now let's replace this by some other elliptic differential operator. Now it depends where you come from. If you come from spline theory, you would probably prefer something like the biharmonic operator, which is related to thin plate splines, so that's a 2D version of cubic splines. If you come from diffusion filtering, you would like to look into nonlinear diffusion equations, either with a scalar valued diffusivity or with a diffusion tensor, which tries to smooth mainly along edges but not across edges. So you have different opportunities here to select operators, and we have evaluated lots of them. These are just 4 representatives, but they show you what's going on typically. So here's an example that is motivated from psychophysics. This is Kanitsa's triangle here, where you actually have removed most of the data, so you are supposed to see or to reconstruct your triangle, and the data are just given at these 3 disks. If you're using our good old homogeneous diffusion in painting with a LaPlace operator, this is what we get. That's certainly not that good. Biharmonic is a little bit better, but it's still far away. And those of you who remember that I always say the worst in painting you can do is TV in painting. Here we go. That's TV. It completely ignores the data. It just keeps here the small amount of data. You can't do worse with any reasonable operator. And that's just the total variation limit of nonlinear diffusion with a scalar value diffusivity. If you use anisotropic diffusion with a diffusion tensor, which actually diffuses along edges, you get something like that. And that's surprising. So actually we have been trying to optimize operators for about 10 years, and we could not beat anisotropic diffusion. So let me show you a little bit more about that operator. So it's a pretty old story. It's about 21 years old. I initially introduced it for denoising, and we are using it for in-painting since about 10, 11 years. And the idea is relatively simple. It's actually an integral differential operator because the U sigma is a Gaussian smooth version of U. Sigma is just the standard deviation of the Gaussian. So it's a Gaussian convolution. Convolution operation is, of course, an integral. And this tensor, it's a 2 by 2 matrix. It adapts itself to the underlying image structure in such a way that the eigenvectors are chosen along or orthogonal to the gradient of your Gaussian smoothed image. So that means basically you want to smooth either along the edge or across the edge. And secondly, the amount of your smoothing or the amount of your interpolation is given by the eigenvalues. Along the edge, I want to interpolate with an eigenvalue of 1. This is large. And across the edge, I want to interpolate with an eigenvalue which is decreasing. It's decreasing with the contrast. So that means the higher the contrast of my edges, the more I want to decouple my interpolation problem. And this is kind of a regularized and rescaled TV diffusivity, that's all. So it's closely connected to TV actually, but it makes TV anisotropic, and in particular it allows to in-paint with a full amount along edges. And this is a second order differential operator, integral differential operator. It gives rise to max-min principle, so that means it's relatively easy to handle. And let's try to understand why it works well. So here's a little example. I told you I'm always aiming at driving things to the extreme. This is one of the most extreme scenarios I can think of. I specified just 2 pixels, a dipole. And outside in the gray area, nothing is specified. And let's have a look what this anisotropic diffusion does to the dipole. So you see it propagates information to the neighborhood, and it actually creates a separation into 2 half planes. So a dipole is sufficient to encode a half plane. Okay, that's the first observation. And some of the people at the workshop have cited Weickert rabbit. So here's the so-called Weickert rabbit. So I have removed most of the data of a binary image which contains some shape of some animal, and what you see are just 24 little disks, and so these are the disks where the data are given. And now let's run anisotropic diffusion in painting on it. And you see the rabbit is a cat. So some people find this quite remarkable given the fact that this is essentially a second order differential operator, and they have been struggling a lot, for instance, with Elastica to do something similar. So why is this so good? So here's my explanation attempt. So first of all, it's an anisotropic operator. So that means it is able to perform in painting mainly along one direction. That's of course very useful if you would like to reconstruct edges without specifying too many data. So I'm saving data for specifying an edge, and I could use this data beneficially somewhere else. Then I have this Gaussian convolution, which of course is a small way of, is a simple way of introducing some sort of non-locality. So if I measure locally some anisotropy, I can communicate it towards my neighborhood, so I can propagate anisotropy. That's the one benefit of it. And the second benefit of it is actually Gaussian convolution has also curvature reducing effect. You can use it, for instance, for simulating mean curvature motion. This is well known since more than 20 years. So actually it's not surprising that I get here some curvature reduction properties. And we also try to justify it from the statistics of natural images. So there's a paper which links it to the statistics of natural images, showing that the image statistics actually suggest to use some sort of anisotropic operators for in-painting. And I would like to advertise this as a serious alternative, for instance, to Elastica, because unlike Elastica, it's not a fourth order evolution, it's a second order evolution, but integral differential evolution. So the integral, the Gaussian convolution, is the replacement of incorporating some sort of curvature information. That's of course more stable and easier to solve numerically, and also it's easier to come up with faster algorithms. And the experiments that we have been running, so Tom and I, we have been actually comparing a lot over the last 3 weeks, suggest that it's at least not worse than Elastica. In some cases it's even better, perhaps because it's easier to come up with good numerics there. Okay, so that means we have a good candidate for in-painting which can beat homogeneous diffusion, namely this edge-enhancing anisotropic diffusion. But that's not the entire story. So what we have learned is, okay, homogeneous diffusion is fine if you are able to select your data carefully and optimize it carefully. This anisotropic diffusion, this AED, is pretty helpful if you would like to reconstruct edges from a few data only. That means also for textured image structures. And that means if you need less pixels at edges, you can use them beneficially somewhere else, so you can distribute your data more evenly, or in other words, you don't rely on the fact that you have to specify your data on edges. So that indicates that this operator is more robust under less optimal data selection, and we could exploit that. We could exploit that in such a way that we say, well, if this is robust with respect to the data selection, then perhaps I can be less critical with the data selection. Then I can choose my data in such a way that they are cheap to buy, and therefore I'm still doing well with this EED because the data are cheap and EED does a good job. So that means we are looking at a perhaps suboptimal strategy for data selection which is highly efficient. And here's a proposal which works fine in our experience. It's a simple subdivision structure. So we start with a few pixels and we measure the approximation quality here in the interior of that rectangle. If we are not satisfied, we subdivide the rectangle along its longer side, and then we measure here again. If we are not happy, we subdivide again, and so forth. And that just means introducing an additional pixel is just one subdivision step in a binary tree. Or in other words, it's a binary decision, so I can encode an additional pixel on average with something like an effort of or cost of one bit per pixel. That's a good price. So you can easily buy those pixels. So the main question is how good or how bad are they if I combine them with this edge-enhancing anisotropic diffusion. Of course, in order to come up with a full codec, I have to do a few more decisions. This is more engineering, so I don't want to go into too many details. Essentially, we quantize also the gray values. We quantize them in a coarser way to save bits. And actually, we use short bit strings for words which are more frequent. That's what we all do. There is a reason why words such as yes and no are so short, because we need them on an everyday basis. That's entropy coding from an information theoretic viewpoint, and this is what you get. So let's take the image of the lady again, and let's aim at binary subdivision here. That is one which actually shows you the data in such a way that you get compression rates of 57 to 1, and the result which you get is this. So if we compare this now to JPEG and JPEG 2000, once again, that's the original image. This is what JPEG gives you at a compression rate of 57. So you clearly see the blocky structure. This is what the wavelet-based JPEG 2000 gives you at 57 to 1. And this is what anisotropic diffusion gives you. So suddenly you're better. If you use all these tricks and if you optimize your data and your operators, suddenly you can beat JPEG, and you can even beat JPEG 2000. So once again, also here it's interesting to see how far one can go. So we actually looked at compression rates up to 260, and that was JPEG 2000 at 260. I guess most of us have difficulties to conjecture that this shows the picture of a lady. At 260, you can still do well with anisotropic diffusion. So that's the point where you have to admit that Osha was wrong. You can beat JPEG, and you can beat JPEG 2000, at least for specific images, using essentially nothing else but concepts with PDEs. Okay, so that's the main story, and now let me tell you a little bit about variations, connections to other fields, and adaptations to certain specific problems. First of all, I would like to connect this a little bit to sparsity. Sparsity is something which is very popular since about 10 years. Actually, selecting a small amount of pixels is intuitively something which has something to do with sparsity. That's clear. You can make this more precise if you look at what is called the Green's functions of an operator. The Green's function of an operator is the function that under the operator gives you essentially the delta distribution. So that means it is somehow related to an impulse response. And you can also derive this in a discrete setting here for discretized problems with homogeneous Neumann boundary conditions. So we came up with discrete Green's functions, and it just means that you can assemble your solution in terms of these Green's functions by seeing the Green's functions as atoms in a dictionary. And this dictionary aims at a sparse representation. That's what we are doing. So it's closely connected to sparsity. Your specific atoms are the Green's functions. And depending on which operator you choose, they look quite differently. So for instance, with a Laplacian, you get Green's functions which have a logarithmic singularity here. That's in the middle of that's in the center of your image domain, and if you go more towards the boundaries, it's a bit distorted, but the singularity remains. If you aim at the biharmonic operator, you get a C2 solution, so it's way smoother. So you can design your Green's functions using this framework, and that even has numerical implementations because you can design them with a discrete cosine transform, and that means you're using the same weapons as JPEG. And that means also numerically you can do this as quickly as JPEG or JPEG 2000 suddenly if you use linear differential operator. So that's the next way we are aiming at here. Then it's easy, if you've understood anisotropic diffusion, it's easy to generalize this to 3D. So this is just a section from a 3D data set from medical image analysis, a trabecular bone set. If you compress this with DICOM, that's the standard there, it's essentially a kind of JPEG 2000 slice-wise. You get here at a compression rate of 200, you get here an error of 65. If you do this with edge-enhancing anisotropic diffusion, you get an error of 38. No? So also in 3D it's helpful. If you think of the LaPlace operator as an in-painting operator, it's relatively simple to generalize that to surfaces. Just replace the Laplace by the Laplace-Beltrami. So that means also in geometric modeling you can use this. This is joint work with Egil Bahr. So we have taken the face of the head of Max Planck, and we discarded 90% of the data, also at those points where the curvature was lowest, and from the remaining data we could reconstruct the face in this quality. Often you are also facing situations where you know your data are piecewise almost constant. This can be used in a pretty beneficial way. So here's an example. That's a sign at Svalbard which warns you of black polar bears. And well, a typical codec, which is also in accordance to the analytic theory, would just suggest to keep the data left and right to the edges, because these are the locations where the Laplacian magnitude is largest. So you can do this literally. You keep your data here at both sides of the edge. You can also sample them there because they're varying very slowly, and you can also entropy code them in an efficient way. And then you come up with something which is really competitive, because this is the result at a compression rate of 200 to 1. Using homogeneous diffusion, not even anisotropic one. How does this compare to the usual candidates? So here is the original image. This is JPEG at 200 to 1, JPEG 2000 at 200 to 1, and homogeneous diffusion at 200 to 1. So at least for these piecewise constant or almost constant images, that is something which is relatively natural. If you have something like piecewise smooth images, that's a bit more challenging. The proposal we have in such a scenario is to combine diffusion in painting with a segmentation. So if we are able to come up with a simple, it does not have to be a very good segmentation. So we use this as boundaries for our in-painting process. And inside an object, the gray values are varying very smoothly, so I can essentially use a regular grid. I don't have to adapt the grid very much, perhaps only at a few locations. So essentially a pretty regular grid combined with the segmentation can be good for piecewise smooth data. These are depth data here from a breakdancer sequence. And let's compare this. So that's the original depth map. And here we compress it with a rate of 177 to 1. So this is what we get with segment-based diffusion. So it's basically the same, original, compressed. This is JPEG 2000, that's a bit worse, and JPEG is substantially worse. No? Okay, and of course, we have our hardest time if an image is fluctuating a lot, if we are suffering from a rich texture. In that case, we are combining PDE-based in-painting with exemplar-based in-painting, where we basically reproduce texture patches, or it's just another word for copy and paste, basically. And if you do this in an appropriate way, you can actually improve this edge-enhancing anisotropic diffusion a lot. So here you see that this suffers quite a bit here, so this rich texture gives us a hard time. Combining it with exemplar-based in-painting also gives you good results in that context. Of course, this is not real-time capable yet, but it's a first attempt in that direction. Yeah, this is just for the sake of, this is just for the fun of doing it. We have a colleague in cryptography in Saarbrücken, and we thought we could do something on censoring. So we want to censor an owl. How do you censor an owl? Well, the same way as if you censor humans, you just remove the part around the eyes of the owl. No? Okay, what I have really done here is I have taken this part, I have encoded in a compact way in a bit string which can be decoded with anisotropic diffusion. So I have basically just compressed it, and I have redistributed that part in the feathers here, in the least significant bits of some selected pixels. The least significant bits are called least significant because you don't see if I manipulate them. Huh? And if you know a password which tells you where I have hidden this data, I can reconstruct the O like that. Huh? It's just a funny demonstrator, that's all. But if you want to play around with that, feel free to go to our webpage, stego at MIA, Mathematical Image Analysis, uni-saarland.de. You can upload your image, you can try to hide it in another image, or you can even try to hide a large image in a smaller image by compressing it. It's just for the fun of doing it. Okay, then a master student was asking me for a topic for master thesis, and I had a one sentence description for the topic. I just want to see a vampire movie at our Christmas party with anisotropic diffusion encoding in real time. So that's the project description. So it was spring, so the student had about 9 months to do it. And that was the vampire movie I have selected. It's a grayscale movie, so I don't care about color. It's an old movie, so I don't care too much about quality. It's a silent movie, so I don't care about the audio tracks here. Nevertheless, the student managed, so we can play this in real time with anisotropic diffusion in painting. However, you have to play lots of tricks. You have to use the GPU of the PC, and you have to come up with parallel algorithms. We have developed so-called fast explicit diffusion schemes which are able to do this, and it's possible to play the full movie of 49 minutes in reasonable resolution given the quality of the movie with 25 frames per second. So that's the demonstrator that edge enhancing anisotropic diffusion is fast enough to do this even in real time if you are allowing a GPU. If you don't have a GPU, you can still do it on a CPU with homogeneous diffusion. And of course, this is just frame by frame, so I have not used any temporal coherence of a video. That's what we do next. So Sarah Andres, a PhD student in our group, recently came up with a full codec which also uses motion information, and that means temporal coherence in videos. So we use the concept of optic flow, of variational optic flow. So we code a few frames in full quality. So these are the so-called intra frames. And in between we code the motion field in a coarse and a subsampled way. And with that motion field we can warp the image and try to predict the motion of the frames in between, the so-called interframes. Of course we do an error here. So we have here a residual map which we can also encode using homogeneous diffusion, for instance. So that means it's a fully in-painting based video codec, so the first which tries to do this, and that means it's also possible to go in the video direction, but this is certainly one of the biggest challenges for us. Okay, and that brings me basically to the end. So I just wanted to convince you that perhaps there's more behind PDEs than just solving problems in physics or some standard problems in image analysis. You can even try to compress visual data by exploring the in-painting, that means the interpolation capabilities of PDEs, because these operators are connected to the statistics of natural images, so they are good in-painting operators. And from a mathematical viewpoint, you are facing lots of interesting optimization problems, data optimization in a spatial setting, in a tonal setting. You have to optimize your operators. You can also optimize your encoding, and that's of course a very challenging task. And you saw also that these ideas can be modified in many ways, and they are widely applicable. Yeah, what about our ongoing and future work? Well, one of the big challenges is to treat all optimization problems simultaneously in a unified way. So we are simultaneously dreaming to optimize the data, the operator, and the way of how we encode the data. That's a very tough problem. That is something where we definitely need a few more years to come up with good results. And the bigger challenges are still texture, how to deal with highly textured images, and in particular how to do this also quickly. So that means also the numerical issues, coming up with highly efficient numerical methods for parallel architectures is a challenge. So I have promised in that ERC grant that we will come up with a 4K real-time player using these PDEs. So that means we have to speed up our methods by a factor 100 in the next 5 years. So that's the challenge we are trying to master. And that's it basically from my side. If you're interested to read a little bit more about that, here's the web page, and there's also the QR code for those of you who just want to take a photo in order to go to the web page. So thanks very much for your attention.
Thank you very much, Joachim, for a fascinating presentation. Questions? Mira?
You presented several different ways of encoding according to the image. Is there a way to decide, if you do not know the image, just to decide what is the best way to do for random image?
You have to find good criteria, basically. But actually, that's what all the codecs do these days. So, for instance, the video codecs these days, they have lots of opportunities, and they try them all and select the one which works best. That's just because we have the computing power these days to be better. They try out several options. And of course, my goal is to do this in a bit more systematic way, perhaps to come up with some good measures which tell you, okay, this image is highly textured. We should employ also exemplar-based in-painting here, and if the image is piecewise almost constant, we can do it in a simpler way. In general, of course, the more you know about an image, the more efficient you can encode your things. Also, even we are trying to incorporate a modest amount of learning into our methods. Also, learning operators might be useful here in that context. I think we definitely have to become more adaptive, and I mean there's also some work. I mean, you are doing also things like learning the best variational methods for denoising or restoring an image. It goes in a similar direction. You want to find the optimal operator for a given task, and ideally this should be done without any human interaction, so the optimization approach optimizes the parameters as well. So we are also looking into that.
You seem to be mostly focusing on these elliptical operators that have what you call min-max principle. I think of it as a sort of averaging property. I understand the numerical advantages. I also understand that for many natural images this is good. But are you at all thinking about applying operators
Hyperbolic
do not have this property for images that are not so natural,
yes,
as your shirt, for example?
Yeah. Well, actually, many images are not smooth in that sense that they are C infinity. So often a more realistic model is piecewise smooth. So you allow discontinuities, and the typical operator for that would be total variation. That is some sort of minimization of L1 norms, basically. And actually, our best operator, this EED, this edge-enhancing anisotropic diffusion, is using kind of a TV diffusion in one direction. So we are going to a limit where the parabolic operators at least become singular. So if this satisfies you a little bit more. There are also some people who have used, for instance, elliptic operators for in-painting. Bornemann and Merz, for instance. They can be good, but our experience is they are still a bit worse than the parabolic ones. So I would say perhaps if you are clever in using them only at edges, they are very, very good tools, but in between, in general, a parabolic or elliptic one will do better. So that's my personal experience. And you could also think of going to higher order PDEs, but essentially my feeling was, with the experience with this edge-enhancing anisotropic diffusion, you should rather invest in integral differential operators of lower order than going to a higher order differential operator for numerical reasons, and also essentially you keep the benefits. If it's essentially a second order operator with some integrals inside. You still have the max-min principle, which is somewhat nicer than going to a higher order operator where you have much more trouble guaranteeing things like that. But essentially, I'm actually also looking into pseudo-differential operators, which restricts ourselves into a linear setting, but it's not a big issue. All these pseudo-differential operators in a linear setting can be expressed by means of the discrete or the continuous cosine transform, so we can even come up with fast algorithms. So perhaps the next step that we are planning to go here is allowing general pseudo-differential operators, linear pseudo-differential operators, and optimizing them to within certain image areas. So that might be another way to go. Yeah.
So suppose you run your diffusion operator backward in time on your image, and you find corners. And if you run your anisotropic one, you find corners and edges. And suppose I just save those and then run backwards. How does that compare to the more?
It's a good question. I mean, the natural thing when you talk about parabolic operators backward in time, that should ring a bell that it's a highly ill-posed problem, so it's dangerous like hell. But 3 weeks ago I gave a talk exactly here how to stabilize some of these processes. So we are also looking into that direction, basically, to see how far we can go into the backward area to sharpen certain details. And it's clear, the better I am here in finding good details, good structures, the larger is my chance that I can come up with good codecs, essentially. So it's clearly not just finding edges or corners, but corners are and edges are important. And I think my very personal opinion about that is the following. Since 1935, people know that we have in-painting mechanisms in our brain, which are very similar to homogeneous diffusion in-painting. And we all understand comics, cartoons, we can read these things. That means edge information is important for us. And it makes perfect sense that it's also important for this codex. That means we are just using computer vision concepts which are borrowed from biology. Perhaps we don't know all the details, but we copy many of these ideas. And so I'm not surprised at all that perhaps we can do much better if we try to learn much more about that. And the fact that the optimized pixels which we get are left and right to the edges confirms basically what nature is doing. If we have to draw a picture, we just draw the edges. And that just means we reduce the essential information to what we think that using our in-painting mechanism in the brain is the most efficient thing. And it's not surprising that a computer works in a similar way. So this in-painting based codex, in my way of seeing it, is just a way to be a bit closer to biology. The standard ones are using Fourier transform or wavelet transform. This is, at least for me, less intuitive and I think also less biological in some sense. So I think looking more into biology and finding some good features, also corners and junctions, might be very useful here. Yeah. It's a good idea.
Yes.
Intuitively, if you use the Laplacian to do the interpolation, you must get blurring. But it seems that from your result, that never comes out. Can you tell the secret about that one?
Well, I do get blur. It's very simple. I get blur. No? If you look here, I get blur, but I get blur inside the domain. Inside the domain, everything is perfectly smooth. But at the discontinuities where I specify my Dirichlet data, I allow to violate the smoothness assumptions. So basically, the trick is you refrain from smoothness by specifying data points. And that means that's the reason why you have to specify data points where the curvature is high, and that means where smoothness is most likely to be violated. But in the interior, I still get smooth solutions, yes.
here you do the edge. The edge is already known, but for all the later examples, you don't select all the edge. You only select a few points. So that should introduce more diffusion than.
Yes, yes, it is clearly. I mean, if we just look at these stories, no. So we are clustering the pixels near edges, no, and of course, if I'm sparsifying the pixels, I get gaps in these edges, and I also introduce some errors. I introduce some blurrings, but as long as my pixel density for homogeneous diffusion is sufficiently high at edges, the error is under control. It's clear if I sparsify too much, then I'm also destroying the edges, I'm also smoothing over the edges. Therefore, it's natural to connect these homogeneous diffusion approaches with storing data along edges, along contours. That fits very well, and actually contour coding is not that expensive because data is changing quite slowly along a contour, and in that respect I can just code differences or I can do some subsampling. So that means it's actually a pretty good tool to use edge information. You can do the same story also with edges, no problem. Now it's German. That's the talk at my previous school. 30 years after my A-levels. Here we go. Just a moment. Let me just go. This is now a contour-based codec. You probably like this even more because this nicely encodes the contours. You can do this basically at the same frame rate as before. It's perhaps a bit more consequent, but it assumes that you are basically exploring an edge structure, whereas the other one is trying to optimize the data. No? So this is from an approximation theoretic viewpoint, it's a bit worse, but essentially it's just as simple to implement as a pure pixel-based codec. Yeah.
So this is done color by color, channel by channel.
Yes, because it's homogeneous diffusion, you don't have any chance to couple it. For anisotropic diffusion, we are trying to put more brain into the process. You do some sort of coupling, and you can actually play the same dirty tricks as JPEG does. You go into YCBCR color space, where you have a grayscale channel which you encode with higher precision, and the chromaticity channels which are encoded with low precision. So we have specific codecs also for color images. I didn't tell you about that because I thought it's not so interesting for mathematicians here.
Maybe one last question. Yeah.
For this video compression, you want to deliver fast speed, so therefore you don't want to solve the PDEs very accurately. How do you control the tolerance?
Well, I mean, if you have a standard compression problem, the nice thing is you have the original image. So essentially, you can control the error. So a very classical way is if you have a tree-like subdivision structure, and you are not satisfied with the accuracy locally, you just subdivide until you get a sufficient accuracy. So in that sense, just by subdividing or just by allowing a larger amount of data, you can be more precise there. The other story is, of course, you have to solve these equations also with a certain precision. Of course, you also have control mechanisms for the error there, but our experience is, in general, if you have, for instance, a multi-grid solver, often 1 or 2 cycles are completely sufficient, because you don't have to solve the Laplace equation with a precision of 10 to the power of minus 23. Actually, you can do this with 10 to the power of minus 2, because our visual system is just able to distinguish something like 40 different grayscales. So that means even a quantization to 256 gray levels is an overkill. And that's a standard trick, for instance, also in JPEG, that they are allowing very coarse quantizations because the human visual system can be cheated very efficiently, for instance, in high frequencies. Therefore, the precision requirements are surprisingly low, actually. And that's, of course, a good thing for us. Yeah. Mila?
While choosing the pixels in a JPEG compressed image, can you remove JPEG artifacts?
That's another story. Martin Holler has much more experience in that than I, for instance. Of course, diffusion-like processes or PDEs in general are useful, and they have been used in many ways for removing JPEG artifacts. But then it's good to know exactly how the artifacts arose, basically. If you know a little bit about what the DCT does, how you quantize these errors, that helps a lot. Just using a PDE because you have it in your toolbox is not enough there. That's my feeling about that. Yeah.
Exploring some neighborhoods, you can always see whether there is a chance to have.
We see it, yeah, and I think it's possible to do quite a lot of good work in that direction. At least what I've seen. But the more you know about your problem here, the more you can do as well. Yeah.
It's very encouraging to see. Just once again confirmed how cool PDEs are and how powerful they are. So thank you very much, Joachim,
Thank you.
for this really